So chapter 6 is Vernier Instruments, and so we're going to learn about these instruments. So we use them in tool rooms, model making, and laboratory work. So the Vernier instruments, they include height gauges, depth gauges, gear tube instruments, and protractors. So when you look at the vernier, you're going to see two scales. The first one is your main scale, and the other one is your Vernier scale. So with vernier, you can read to 3 decimals. So first, you're going to round off the reading. So that's select your nearest inch. And then the next one is you're going to select 0.1. So that's your first decimal. And then we're going to read the second about half. So right here. And then we're going to read the third decimal. So here in this case is 2.115. It's pretty difficult to see, so take your time and be patient to be able to see these graduations or discrimination. Okay. So when you look at here, this is your main scale, and then this one is your vernier scale. And you're going to go from 0 all the way to 25. So here in this case, you're going to read from left all the way to right. For this one, is a little bit different because this direction is going from the right all the way to left. Okay, so just make sure where your zeros are on your vernier scale. You have two scales, the big one and the little one. So for vernier instruments, nearly all of them are available with matrix scales, but in America we use decimal inch as well. Okay. Not all of them, just nearly all of them are in matrix scales. So for vernier, if you have like a 50 divisions, then it's easier to use them than your 20 division vernier. And here are the advantages and disadvantages of vernier scales. And they're pretty easy. You can read through it. Amplification is achieved because of your design, and design is so important for vernier because if you didn't build your instrument in the right way, it's not going to give you a reliable measurement. You don't need interpolation, meaning like you don't have to calculate by hand, and all you have to do is just read it. Okay. And there's no theoretical limit to the scale range at all. And the zero setting adjustment is pretty easy. All you have to just close your vernier and then set at 0 to calibrate. Disadvantages is well, lies in the instrument on which verniers are used, the way you use it. Okay. And the reliability of reading depends more on the observer than most instruments. So again, the way you use it, the way you read it, the discrimination is limited, and that is also a disadvantage. And there's no way to adjust for any errors other than 0 settings. So vernier is kind of like a trim, okay, that you put onto an instrument. So here, if you put the vernier on caliper, you're going to get the vernier caliper, and that's a slide caliper with trimming. So when you look at it here, this is your beam, okay, you gotta read it very carefully. So these are just showing you the functional features, and that's your metrological features. And here, when you take a look at it, you're going to see the vernier scale plate. Inside of that is your vernier scale. Here are your jaws. You can do outside and inside measurement, because when you look at the shape, you're going to see, like there is right here on each jaw, you're going to see a little edge right there, 90 degree. Okay, so that's where you put to do your inside measurement. So you can line these edges onto the rim of your whatever you're measuring. And this is your fixed jaw, and that one is adjustable because you can roll it in and out. Sorry. And here on this side is your metrological features. And here our reference point, that's your fixed jaw, therefore it is your reference point. And this is your measure point because you can adjust in and out, okay? And this one is your axis of instruments where you're gonna use it to align your part. Alignment is so important for vernier. So if you remember two measurement methods, we have interchange and we have displacement. So for verniers, the method is the displacement. So every measurement you're doing, you've got three elements. So one is your part, the other one is your measuring device, and then your standard. So here for vernier, step one, you're going to observe one end, okay? So that this is closed position. So therefore we're setting the 0. Vernier itself is your instrument and also the standard, okay? This and that. The part we're going to put it in, so here that's your part. So you're going to observe the second end of part simultaneously with observation of standard. So basically we're doing this. So here how you measure the part using a vernier calipers. So vernier caliper, they don't follow Abe's law. Abe's law is just telling you you can get the maximum accuracy when your standard is in line with the axis of the part being measured, okay? When this standard is in line with the axis of the part being measured, you're going to get the maximum accuracy. But this one, it doesn't follow it. So when you look at here, there's a position error right there. And that's because, you know, this position X is kind of like not in line. Okay, and here this is your line of measurement. So we have Y, position Y has error in measurement 1 right there. When Y is 0, Y is definitely 0. When X is 0 or H is 0, but this condition can never happen. Okay, because even if you go all the way to the end, to the fixed jaw, it looks like close, but that's not 0. So 1 can never become 0. So therefore, this condition cannot happen. So X can never be 0, and neither can H. So here are the steps for using the vernier caliper. I'm not going to read that for you. You can go ahead and read by yourself. It's all about calibration, cleaning, maintaining, and how to use it step by step, right? And we're already doing that. The only thing we didn't do is calibration and cleaning, because I just came into this school like 3 weeks ago, so I haven't actually looked into the instrument yet. But I think the anyway, so definitely need some cleaning to our instruments. Okay, so when you use your vernier caliper, so what you have to do is you've got to be so careful to check your alignment, okay, between your caliper, vernier caliper, and the part you're measuring. So otherwise, you won't get accurate measurement at all. So because geometry is vital to get the reliable measurement. So here is your line of measurement, and this is your reference point, and that is your measure point, and from here to here is your measured distance, okay? And this is your plane of caliper. And so just make sure that you've got that alignment correctly. So here are your 4 essential points. So just trying to tell you that line of measurement is shortest distance separating the reference point and measure point. And if part is rectangular, the line is perpendicular to the reference edges. Okay, this needs to be totally perpendicular to get reliable measurement. Second one is line of measurement must lie in plane of caliper. Okay, right there, same thing. Right here is your line of measurement. So we want parallel to each other. And then line of measurement must be parallel to beam of caliper, the same thing. Line of measurement, this is your beam of caliper. And then 4 or deviations from the above will be included as error in the caliper reading. So if you do it wrong and you got deviations, that's your error. So we start our lab and I ask you to measure cylinder and a water bottle. and I see some people doing it from the site because I told you to go ahead and measure it. So we use the normal calipers, right? Okay, so anyway, if you use a vernier, it's better. Like if you have a flat surface and we're trying to get that measurement for diameter, try to do it from top or bottom, okay? So here you're seeing the caliper from the top of that. So you can only see it's the top of its head right there. So that's your beam top right there. So what you do is you put that vernier caliper onto your part, and then you going to swing, okay, swing around past the center, and then you're gonna hold your instrument, which is your vernier caliper, to just to the center to get your diameter. Okay. So errors come from misalignment. So if you don't do your alignment correctly, you will definitely get errors from your measurement. So make sure you get the correct alignment, even if you're measuring for a diameter, go all the way to the center by swinging around the circumference. So in the lab, I gave you the plastic material because the reason is if I gave you the metal material, you would dent it. Okay, so we don't want that. For plastic, you are definitely careful with your force. So why is because sometimes over tightening can happen. Okay, so this is a correct way, but sometimes you can over tighten your instrument, so you're gonna get curved out like this. So here you can see the edges not aligned, okay, not 90-degree. It's a totally angle out. So we can see C and D right there, and then your A and B right, your A and B right here, okay. So here is your curve, and then we're getting the distance for the difference right there. Now here from A to B is 10, and then from C to D, because of the over tightening, we're losing 0.016, okay? Because this beam, look at that, over tightening causes the beam to bow out. Okay, so vernier, you can't rely on it if you are manipulating during your measurement. Manipulation during measurement is nothing but you're not getting a correct alignment, okay? So here when you look at it, this part is like oversized and that part is like undersized. So what we want is this way, okay, this position. So important. So manipulation of the part and instrument is by far the greatest cause of errors with vernier calipers. So if you want to keep your accuracy and avoid additional error, you've got to check defects, okay? And then you have to calibrate your instrument frequently. Alright, the next thing that you need to know is we have jaws, two of them fixed and adjustable. So we have jaw error, so they can cause plus and minus errors. Don't confuse that with the standard deviation. That's not your tolerance zone. That's just your errors. And that depends on where the part feature contacts the jaw. Okay. So again, you have to pay attention to your alignment because jaw error can cause plus or minus error right there. So here you can see that's your correct size, and then this is your undersize, and that is your oversize. So oversize is going a little bit off. Undersize is like over tightening. Okay. And here you can see your typical wear from your general use, and see like how this is like not perfectly aligned and that's kind of like open. And here is like you have a pocket in between the jaws, and we don't want any of that. Those are all wear, and because they may take very different forms, and they're going to give you errors. So since the design shape of vernier is pretty good, so you can get the high repeatability. This is not reliability. Students usually make mistake here on the test. They always read this as this is repeat. Okay, that's not reliability. That's a repeatability. And if I put like reliability, they always choose the wrong thing, so just pay attention here. So all measurement could be incorrect as well as correct, and that depends on how you measure it. So you gotta do repeatability tests regularly by using your standards of known value, like your gauge blocks, like we're doing in the lab, okay? And your master cylinder. We don't have this one here. So repeatability, accuracy, and precision. So when you look at it, repeatability of one measurement on one part with the same instrument and observer. So repeatability does not measure the accuracy of the instrument. It doesn't measure the precision either, okay? So what it does is it does measure the combined precision of the observer and the instrument, okay, for one portion of the entire range. And then it can also measure the accuracy for the combined, again, observer and the instrument for one portion of the entire range if that true value of the test part is known, okay? And don't worry about it, you will know it as you practice measuring the parts in lab, because repeatability is extremely important. Zero setting is nothing but you're going to close the drawers and then you're going to set at 0 and check if your vernier is reading 0.000, okay, on the scale. And here is your metrological data for Vernier Instruments. So we have Vernier Caliper, we have Vernier depth range, and we have Vernier height gauge, depth gauge, and then Vernier height gauge. So all of them is in metric inch. And here, this is not repeatability, this is reliability. Okay, so you can see their ranges right here. Measurement type is all direct. We have normal range, design, designated precision. Discrimination is your graduation, sensitivity, linearity, and your reliability. Then we're gonna go into dial calipers. It's the one that we have. Both of them we've got it in the lab. And here, this one is your electronic or digital, and this one is your regular dial. Some of them come with a charger. Some of them go with a battery, like we have. This is your vernier depth gauge, and we use it because we can be able to measure the height of the hole, okay, and everything that gotta go inside of something. And when you look at it here, there are several ways not to use your vernier depth gauge because it's not going to give you reliable data. So here, reference line is totally messed up. It's not aligned with your measure line. And here, when you look at it, the line of measurement is not in plane with your instrument. And here, when you look at it, your base lifted off, okay, off of the reference line. And here is a manipulative error, totally off, okay. That's pretty bad. Now this one is a big picture for your dial version of your depth gauge, and they're gonna read all the way to 0.001 inch, so third decimal place. You sometimes call that 1,000, right? 1,000 inch. And don't forget, when it comes to this, is like metric inch. Okay. Then we come to the vernier height gauge. So this one is a vernier caliper with the entire surface plate right there is this fixed jaw. Okay, so this one is completely a base. So the fixed jaw is not a base. And this big thing right there is your adjustable jaw. And you don't even call this as a jaw because it's big, so we call that like okay, and that's your scriber. And this is your two measure points. That's just your observed value. Your reading right there, your reading frame right here, the same thing. and this is your fine adjustment, okay? And this is your main scale. Vernier scale is inside. Then you have your excess of instruments, where you gotta compare your alignment right there with your part. This side is your functional, and that one is for metrological features. So vernier height gauges popular attachments are the scriber, okay, and then we have the depth gauge attachment right there, and then we have the offset attachment and the indicator holders on here. But you can see different sizes, smaller sizes. Here is all sizes, okay. We can also do the outside and inside measurement, so it's pretty good. For offset, you're doing here outside measurement. So the scribe attachment, we commonly use that for the scriber for layout, and for offset scriber we use it. It can be used all the way down to the surface plate, right? This is just showing you, this is your depth gauge attachment, and you can be able to measure, okay, inside of the cylinder. And this one is your indicator holder attachment, another attachment. Die and electronic height gauges. So here you can see the electronic one. For dial, you can see the dial right here instead of your digital display. So this is trying to tell you about the steps for using depth gauge with vernier height gauge, okay? You only have to read it one time and try to know, because we're not using this instrument in the lab. And all you have to know is their name and then their feature and what they're measuring. We're not going to ask you, how to use them at all. So height gauges, they have adjustable main scale that can be set for any reference height. So that's pretty good. And which cuts down the chance for observational and computational error because of your main scale is adjustable. Okay. So if I ask you, oh, adjustable main scale, what does it do? You're gonna tell me it's gonna cut down the chance for observational and computational errors. And try to look at the pictures and try to understand, which instrument is what. So don't confuse with your depth gauges with the height gauges. Okay. I think that would be the hardest part for this chapter. Try to recognize the instrument. So the problem of height gauge, because of its height, it is unstable. So you always get the instability right there. Okay, so you can see here error right there, and here the same thing, instrument error is going on. Here that's your line of measurement. It's not parallel to the column. Okay, and sometimes your measure plane is not parallel to the reference plane. And sometimes you get like a wobble, shaking. So this one just showing a height gauge with enlarged base and massive column here, and usually create measurement problems. It just looks really cool with it. It's not pretty good. So setup errors include dirt, your surface plate error, burr on height gauge base, and so forth, where an abuse can disturb the squareness of the column to the base and of the movable jaws. So if you can keep the height equal or less than this height equal or less than the length of your base, is going to give you more reliable measurement. This is just trying to show you the ratio of base to height. Okay, so here's your measure line, that's your reference line or plane. And here, this is your line of measurement. So when you take a look at it in this part, that's reliable because your base length greater than the measurement. Okay, so you're basically comparing your base length with your measurement, which is your height. That's kind of satisfactory because your base length equal to the measurement again. Okay, your measurement is right there, and this is your base length. So here, okay, here that's what we're comparing. This is unreliable because your base length is shorter than your measurement. Okay, so in mathematics, so we're gonna say like AB is less than XY. That's your height and that's your base. The best and reliable measurement is when this two is equal. Okay, equal, or the base is less than your height. The same thing right here when you choose a support surface. Okay, consider its condition as well as the ratio of base to height. Again, base got to be equal or less than the height. Then you're going to get the most reliable measurement. So that's your surface B, that's your surface A, and that's your surface C. That's your base, and this is your height. Okay, you can also flip it. Here I'm flipping it. So if A and B are better than C, that's reliable. If A and C are better than B, preferred. And if B and C are better than A, well, comparing the support surface, okay, neither is reliable. Then here is a table for suggestions for reliable height gauge measurement, and you can follow them carefully. But in our lab, we're not doing this because we have only one height gauge and it's kind of broken. I checked it yesterday and it was funny. Anyway, so you also need to be aware of the quality of your surface because if reference surface is unknown or poor, it has lesser chance to get reliable measurement. Vernier protractors, we're going to learn about them in chapter 12, not here, not in this chapter. Okay, so the last one is your gear to vernier caliper, and you only have to know what it looks like. So if I give you this and this, then you can be able to identify that is your gear to vernier caliper. So it is two vernier instruments combined. One part is the vernier caliper and the other part is your tongue. Okay. The vernier caliper part is to measure the tooth thickness at the pitch line, and the tongue part is going to travel between the jaws to measure the distance from the top of the tooth to the pitch line of the tooth. But you only have to know, we're not going to ask any of that. So finally, don't forget 3 elements of your measurement. So they are object to measure, and then standard of length to compare with, and then the means for comparison. So accuracy of measurement totally depend on the positional relationship of these 3 elements. Okay, don't forget positional because we're measuring. Alignment matters. Okay, all right, that's it for this chapter 6.